Thank you, Bernardo, for the
Rafael, thanks. So I owe Rafael all my little knowledge of what I'm going to present. I'm not a physicist by education. I know little physics, so don't destroy me if I say some wrong physics statement. I have a lot of mathematics statement. These guys, that's physics. So please bear with me, my little physics. So I wanted to present what is on the title, which was something Rafael asked me at some point. What are the appropriate topological invariants that one can associate to magnetic materials? And really quick, of course, I knew, as Emil was saying, well, it's some K-Q invariant. But one thing is knowing what it is, another thing is to calculate what it is. These are perpendicular things sometimes. So it took me some time, but instead of going directly to that, let me somehow tell you what is this, what I've been doing in the last years with Rafael. So we want to measure topological invariance or some sort of information on something, and the question is, what is the something that Emil was telling us what should be the something. And so a topological invariant is a quantity which appears as numbers most of the times in this condensed matter physics, but it could be more than a number. It could be a group, or it could be a ring, it could be an algebra, it could be many gigantic things. That, but of course, if you want to calculate, maybe it becomes a number. And it appeared first of all as invariant of objects, geometrical objects. And the first famous topological invariant is the Euler characteristic, Euler 1700s. And so what is this? You take a topological space and imagine you have some object without boundary, it could be let's put it without boundary. Imagine it's not filled, so it's a surface, and you triangulate it and you count the number of points, the number of edges, the number of faces, and you do this little formula that Euler told us, and then it becomes constant no matter how you triangulate it, the number is the same. So it's an invariant associated surface. And in this case, it's simply you count the number of holes, you can see it visually, or you can do computation, and it's just 2 minus 2g, and this is the number. So it's invariant, you can just twist, move, you cannot tear, you cannot cut, and it stays stable. Of course, there are other ones. He was telling us today about the fundamental group. So you take R2, you take 2 points away, and you measure how many ways you can put loops around it up to the formation. But then you know that it's not just a set. You can concatenate paths, and it becomes a group. And I put this the fundamental group of the Klein-Bartle, and it's not a abelian group. The integers acting on the integers as a semi-direct product, where the action is just dimension 1. But there are other ones, the homological numbers, the Betti numbers that were discovered by Italian school Betti, which is giving us in today parlance the rank of the homologies, or rank of the homology. And in this case, the Betti number here is 2, because it's telling us that there is a loop here that you cannot contract, and there is another loop here that you cannot contract. And the second Betti number is 1, telling us that there is a two-dimensional object that you cannot disappear. So, but of course there are more. But all these topological invariants, in some sense, are invariants of the object, which is the physical object that I have here, that is some space. But in this talk are going to be topological invariants of what? So if we, as Emil was saying, if we know what we are somehow trying to detect, things may become simpler. So it's topological invariant of vector bundles. This is somehow the commutative version of what Emil was saying. And the first appearance of a nice topological invariant is due to Poincaré and Hopf. First, Poincaré-Hopf generalized it, which is you take any vector field on any object, dimension, like a smooth object that you can imagine, and then you just go and look when you have singularities of the vector field, when you get zeros of the vector field. So here, or in this one, there are only 2. And then if you count the number of singularities, you cannot say much. But if you count the singularities with the winding number, I think what Smith was saying, and you add these numbers, then it becomes again an invariant. So here there are two. One is a source and the other was a sink. Those ones have degree 1. So you add them and it's 1. And here you have a source and a source and a sink and a sink. And this one, I don't know how to call it, a saddle point. And they have 2 plus 2 minus 2, and then again 2. So no matter what you do with your vector field, no matter what you do, it's always 2. The thing is, important thing is that it's about isolated singularities. So this is very important. And no matter what you do, this is the theorem that you cannot come the sphere, because whatever you do, you will have a singularity. So this is one first appearance of a topological invariant. But of course, this was studied in the 1930s, 40s, 50s quite amazingly by a school of people in Russia and Germany and in the US by Chern, which is, this is the idea. So we have some sort of space base on which we have some sections which are fields, let's call it fields, this is called it, or sections as we call it. And we should think of this as the sort of Brillouin zone. And these things, you should think of it in the computational way. You should think of some gigantic vector space where you're going to solve your Hamiltonian. Whatever your eigenvectors of the Hamiltonian are some sort of sections of a vector field. Namely, you have some spaces and some momentum coordinates, and then you give me some element that lives in some gigantic vector space. And the way these sections move around and the way they bundle up together, they make up what is called a vector bundle. So a bundle of vectors. Now, there are the simplest of the simplest, in which the 5 is the reals, not the complex numbers. So around the circle, you can only do 2, namely the trivial one, or the multistand, which gives you, if you just go and measure the holonomy of this, you'll get a -1. And so this is somehow the simplest of the simplest political invariants that appears already in the condensed matter world when you have a cat. You get a -1 when you do the holonomy. And it was started by Stephen and Whitney when they studied these fiber bundles. Then came Pontryagin and later on Chern in Berkeley, who constructed the whole somehow homology classes associated to a vector bundle. And I put it, I'm going to exploit this. But what I'm trying to say is that you have a base. This is the object here. And I want to know what are the invariants of some animal that is here. And these invariants are going to be some sort of obstructions, as Emil was saying, of finding sections of some sort of structure. The structure could be one section, namely one of these ones, or a 2-frame, namely 2 together pair, or a 3-frame, or an n-frame. And it turns out that the last Chern class is measuring the obstruction of getting one section that is never 0. That's why I put this little drawing. Green means that the vector is 0. And we want to avoid the 0, as I told you in the Poincare-Hopf theorem. We want to avoid the zeros of the vector field. We don't want them to be 0. In some sense, when we do this thing computationally, they're never zeros because we do this pointwise. We don't do it continuously. But if we were going to do things continuously in finding sections on our Hamiltonian, then we may have a lot of instructions to find sections. But what is the first Chern class? The first Chern class is the obstruction to find a frame of all the vector bundles in itself. So this is somehow the way Chern already put it in his original paper. And if we want a vector bundle to be completely untwisted, namely that is just, everything is just the base and the fiber that is completely the same all over the place, like in this one. For that to happen, all these Chern classes has to be 0. So a trivial, say, bundle, a trivial way in which the sections are bundled up implies that all these things must be 0. And so these are obstructions for finding some sort of sections of some sort. And of course, it's related to the topology, of course, of the base, but also together how the fields interact. So, and how is this somehow done, which of course you all know, I'm the one that didn't know. So it took me some time to understand what the hell are we finding invariants for. I just, invariants of what? So it took me a lot of time because Rafael said, well, this and that. But this is a baby picture of something that you will learn, I don't know, first class in physics. But it's, which is, we take our crystal structure, which is what Emilio somehow was telling us. This is the object on which we want to do the topological invariance, and we want somehow to understand somehow the way it gives us some periodic objects, or the way it interacts with each other. And because what we think, instead of having the crystal structure, well, let's just associate with a Hamiltonian, the interactions of the electrons of the nuclei. But of course, you want to do that for all these 10 to the 26 items. We're not going to do anything. So we do something that I'm going to put it in just 3 letters, density functional theory, that we're going to do some expected values. So I'm going to do, instead of 10 to the 26 atoms, I'm going to do some integral of all the states. I'm going to do some expected values, and I'm going to do statistics in some sense. But these statistics are so robust because of the way the electrons can survive in different orbits, that doing this expected value, which would give us some sort of spread things, well, it's completely localized. It's very nice. So, and this gives us this this spaghetti thing. The first time I saw this, this is spaghetti, I don't understand it. This is spaghetti. And I didn't see anything. Of course, it took me some time with Rafael to train me to see things. I didn't see absolutely anything. And so this is just an image that it's very powerful, but at the same time, it's very distractful, this image. Because this image can lead you to wrong conclusions because it's a projection of a lot of information. You're just projecting the energy, and you're just projecting specific paths that are chosen because of the higher symmetry. But many things are left out, and that could somehow trigger wrong conclusions. Nevertheless, it's a fantastic image of the eigenvectors of the Hamiltonian. There is a specific way that is still a mystery to me, how computationally I find the Fermi level. I don't know. If you ask me how to find the Fermi level computationally, I have no clue, just from the interactions of the electrons, I don't know. But there is a way, and then we want is somehow crystals. I want to study only those ones for the time being, on which we have an energy gap. Because in those ones, I could associate we could associate topological invariance, or invariance of the eigenvectors of the Hamiltonian bundle up together in a vector bundle. So having said this, as Emil was saying, what can I get from this picture? So I'm just going to do 3-dimensional objects. So I have a periodic crystal, so I have a fluid momentum coordinates. I only have 3 directions of movement. They are periodic, so this is just as one sort of circle, or periodically in one direction, periodically in another, periodically in another direction. My eigenvectors all bundle up together, construct something that is a vector bundle, and my solutions of the Hamiltonian equation will give me sections, and then I could go and calculate whatever topological invariance I can imagine of this, of the complex vector bundle. But of course, as Emil was saying, this is just an image of the real space of possible Hamiltonians, which is where you have to live, not here. This is just some sort of an image of some sort of object associated to this universe of Hamiltonians, but sometimes it's easier to figure out that if you perturb a little bit the Hamiltonian, you're perturbing a little bit this vector bundle, and then you can think that you're living here. But what can I get from a complex vector bundle? So simply imagine we only have complex numbers, we don't have any symmetry to anything, we just have the Hamiltonian and we solve it. The only thing that we can get are the Chern numbers. This is the only thing that if you give me a vector bundle, this is the only thing you will hook up. And I must say that if one looks at the mathematics definition of the Chern numbers, or the Chern classes, it's bewildering, it could be complicated to read them, but fortunately, there is this fantastic way to do it if you have a complex vector bundle, which is still there. Which is, of course, one can always argue that Chern knew it if you just do it, if you just somehow take these sections and apply his formula. But sometimes it's good to have a very simple description of how to obtain a Chern class. So, and what are we measuring here? We're measuring here, if you can just read it, how these eigenstates are changing and with respect to the others. And this is what the Berry connection is keeping on itself. What is amazing is that this Berry connection has a curvature, which is the Berry curvature, which is just the derivative, which I wrote it, and I tried to, if I did my indices is correct, this is what it is, it's not, correct me. And the thing is, the whole curvature has all the Chern classes, not only the first, the second, it has all. But if I want to get only the first one, I just take the trace of this tensor and I just integrate it on the surface that I would like to integrate. Since we are in a three-dimensional manifold and we have this vector bundle, and we are not working with negative K0 invariance, which is the K0 invariant, so we are only getting Chern classes on surfaces. So all this thing tells me you can only have, let me see, put it, you can only have 4 numbers, which is giving me your rank. That's the first thing that this is an invariant. Of course, if you add an extra eigenvector, then it has to process some gap. And these 3 numbers, and this is it in some sense. And I remember asking Rafael, why are there no 3-dimensional crystals whose any Chern class is not zero? And well, there are some reasons to understand it if you have time reversal, but if not, well, we haven't seen any Chern insulates with 3 dimensions so far. I don't know why. So then, of course, these Chern numbers, you know them more than me, and amazingly work with these people that connected to, from the beginning on, completely unrelated objects. Perhaps nowadays, if people learn this, they learn it like this, so maybe they don't notice that it was a gigantic way to get to here and notice these things. And nowadays, it's a result that you can just say that the quantized non-conductance is just quantized by the chance. But nevertheless, if you go and look how they got to there, it doesn't look that you're getting there unless you know both paths. If you know both paths, then you see, oh, of course. If you only know one, good. So this is the first appearance of a topological invariant, completely somehow understood in the mathematical world, let's say, but it appears completely canonically physically. So consequential topological invariant, the first one that is consequential, because one might argue what you need Chern classes for, no? But okay, here, the first one. So let me just try to, there was a student here, he left, Jackson. I wanted, but nevertheless, we can always be students. What I want to portray is that we need to find topological invariance of the appropriate moduli space, as mathematicians would say, of Hamiltonians. And this means that you need to tell me, as Evan was saying, you cannot just move your Hamiltonian or as you wish. No, you have some restrictions of movement of your Hamiltonian, namely you have some restrictions of movement of your crystal, just right here. And so that means that not any Hamiltonian can be perturbed in any direction that you want. You may perturb it in a specific ways, namely you either preserve the symmetries or you want to put some like rubbish, but very little. You cannot just do anything, because if you do anything, you don't have any invariant. So what I want to show you here is this very simple first Chern class that appears on this KP Hamiltonian. Perhaps the easiest way to understand a Chern class, which is when you construct this very nice Hamiltonian, and then you want to solve the eigenvalue problem, and then you see that if you want to, if you follow this section across the sphere, if you try to follow which sphere, there is no sphere here, but then this is how it looks like, the energy, but of course we have some singularity in 0, the Hamiltonian is completely trivial, and so instead of trying to see there what's going on, we go around the singularity and we see what happens with the singularity. So so I put here a sphere. This circle is a sphere because we are in the three-dimensional world. And in that sphere of, say, radius 1, the energy is constant, so there's no problem. There I have negative and positive, namely these things in here. And I could diagonalize my Hamiltonian in that universe, where I could just find the eigenvectors. And if I see what is the eigenvectors, I see that there are singularities. This phi here is the singularity. And so I could perhaps On the bottom of the sphere, I have the field, but if I go to the top, this field winds around one time or n number of times, and this winding number of, or this singularity of the diagonalization for the vector is what is the Chern class. So in this case, because if just y goes around once around the singularity, then the parallel is 1 or minus 1. Well, the signs might be wrong, but the point is we can just put an m. Maybe it just simply change the Hamiltonian, and we think, like Rafael told once, oh, we just need to go around m times, and then this will be the Chern class m. Yeah, somehow you just put an m. Now you might think this Hamiltonian, what's the point of it? It doesn't appear physically, well, it appears, but you need to just level 3 perhaps, I haven't seen higher. And you do the whole thing again, and what happens is that you end up with a little m. And this little m tells you that, again, if you have this vector on the bottom of the sphere and you try to move it on the top, it winds around m times. So you cannot fill it in, but it winds around m times. And so, of course, one direction is linear, no, in K. You only see the problem in the other directions. And that's what I said when you picture this energy bands in the specific lines. You might only see this one, and you may not see that one. And then you might think, oh, it's just parallel one bipoint, but they might be of another degree. So I did this little game with GeoGebra because I didn't want to use Python. So I said, well, what is allowed and what is not allowed? So I'm not going to be allowed to change topological invariance. If I change topological invariance, I'm leaving my modular space of Hamiltonians, or if you want, I will have to cross the Fermi level with the other. So I do the simplest of the simplest for our topologies, a linear combination of two Hamiltonians. I'm not going to do complicated things. The simplest of the simplest is a linear combination. Just start with 1, in t equals 0 you get this one, in t equals 1 you get this other one, and you move it continuously and see what happens. And it turns out that if in one you have a causality 1, and in the other one you have a causality 2, at some point you need to jump. And if you need to jump, the only way you can do that is because you don't have a vector bundle anymore. And if you don't have a vector bundle anymore, it's because you could not define it. You could not define it because you have singularity, you have singularity. You have a crossing of the energy level, so it's not an insulator anymore. And in this other picture, you might see a picture. So it's nothing. This is a sphere, and then I have flux 1, meaning that I have Chern class equals to 1, and I move the time from 0 to 1, so I have a sphere across the interval, so I have a 3-dimensional object, and I have here this flux 1, and while I'm moving the time, everything is okay, insulator, pluck. At this point I have a crossing with the 0 level. I added a while point that has this Chern class here, and this 1 plus 1 will give me the other one. But then if I imagine that I'm in the world of the Hamiltonians, which is of course not this is just a picture, my Hamiltonian can move around here, the other one can move around here, but there are some phase transitions which I cannot cross. So in my universe where I can move, my Hamiltonian has to live here. And so what I want somehow to give you the idea is that I have some universe of Hamiltonians that I can move around. And the topological invariance will put walls around them. And it will tell you, you cannot leave this room, because if you leave this room, you will change some topological invariant. Now, the question is that these topological invariants, although embedded all of them in the sister algebra, you need to somehow tell me what are they, how do you calculate it? Now, of course, we go back to Wigner and von Neumann, which I always like to go back as far as we can, and they already told us that if you want to study or you want to get rid of degenerations in the Hamiltonian, you can always do that. That's an easy thing to do. You can just take any whatever Hamiltonian and perturb it, and then you will uncross all the crossings. Unless you cannot do it. And you cannot do it because either a symmetry blocks you to do those perturbations, or because some topological constraint of the total space blocks it. So the Hamiltonian I had before, this very nice Hamiltonian, of course you just perturb a little bit and you open the gap. But maybe you can't. So it's either you can't because of some symmetry or because some topological constraint of the topological space. And so I need to bring the symmetries. And I did this picture because I could not find it anywhere, and Emil might tell me where is this picture coming. But so what are the geometrical symmetries that we can bring in? Well, we have, as Emil was saying, translations. These are the Galilean symmetries. You can translate and you can rotate. Any symmetry of R3 that respects the metric, the Euclidean metrics like this one. And of course, our crystal will have some sort of a lattice associated to this, namely the symmetries of my crystal, which is this gamma, will have some translations. You choose your axis of translations, and then if you quotient by those, you get what they call the point group symmetry. This point group symmetry might have a section or might not have a section. So you might think that a section is symmetric, not it's non-symmetric. But this is the group without taking into account the spin. If you take into account the spin, we need to take the spin group over the orthogonal group, and then this is a Z2 cover. And then we just lift our symmetries on the bottom to the symmetries on top, and this will be, this gamma hat will be our group of symmetries of the crystal taking into account the spin. Whatever that is, of course, we can divide by this by taking the periodic part, and then we keep track of the point group symmetry, which is not this one, it's this G hat. So this is the group information. And this group information works amazingly well in the blocks construction of the momentum. But there is a interesting thing that wants to take into account that brings us the twistings in K theory. That is precisely when I do a partial translation of my eigenvector, then I end up with a face. And this face is what brings the twistings of all the K theory that somebody was mentioning before. And so I'm going to talk about these skew rotations for a moment. And then we have this CPT3 matrix that in our context, and you might correct me, in the ones we're dealing here, we have time reversal or some composition of time reversal with something. This is always the case unless something strange happens, that there is no symmetry of time reversal or time reversal with something. Meanwhile, the particle Hall symmetry is a symmetry that somehow flips the Hamiltonian, and that's something that we don't see commonly in these crystals. So this might something that appear locally, but not appear globally. And of course, the chiral symmetry, which is the composition of the previous two, which is you might see completely a copy of the Hamiltonian on the bottom and the top. Now, what makes the story interesting is that this operation is anti-unitary. Changing t in e to the et simply -1 is a conjugation of the complex number, and that makes the game amazingly interesting. This is what makes this amazingly interesting. So this leads to the tenfold way that I will explain in a second, and I tell you how to understand it. But before going there, let me tell you some application of the previous information that Rafael and I did, that I believe is nice to have a game here and then bring the materials. And any physical question that I don't understand, we might ask Rafael. Because so the thing is, we want to see, or we wanted to see, and this was my first approach to the physics with Rafael. Rafael told me I want to understand some information that is appearing in this type of symmetries, screw symmetries, namely you rotate and shift, so that when you do it n times, then you move a whole lattice constant. And so non-symmetric. This is the non-symmetric case. And so Rafael, actually me. This is the non-symmetric case, and some interesting patterns were appearing in the axis of the rotation. And these interesting patterns, especially this one, somehow we were interested to find them. And it turns out that these patterns is just an image of an irreducible representation of the group on the path. And this was known by other people. And it happens because the following, we simply take the rotation, 6-fold rotation, but because it's non-symmetric, we have this phase. And this phase is what brings the game to play because it changes the phase when we move along the path. So we localize on the path that is fixed by the rotation. And let me show you what we solved the eigenvalue problem. Simply, we had a minus, and we take the 6th root of -1. How many roots do you have? You have 6 roots. And then, of course, you need to divide by this t to the 6. And these things that we're doing is completely local. This is not global. Global is not possible to be done because there's some instructions, but locally we can do it. And since we have the solution somehow, these numbers is what matters, then we can go and see what happens first on the fixed points by the time reversal symmetry, which is that in one case q to the 6 minus this value, and the other one q to the 6 is positive, which this is just because q to the 6 has this specific thing here. But of course, we have this what is called Crumb's rule, because we have some quaternionic representation of the time reversal operator. And it turns out that the values at when we have an eigenvalue of the energy and we apply the time reversal, of course, we get another eigenvalue of the energy, but it turns out that it's a different one, but moreover has a conjugate eigenvalue from the original one. And this is the key fact to now glue the thing. So whenever we have an eigenvalue of the Hamiltonian in the fixed point set, we take the eigenvalue but of the other operator, which is the rotation operator. And once we have that, we can apply time reversal and we get a pair. And then we have this little diagram, which is just a combinatorial diagram. Namely, you start with whatever you start with one here, say, this is the number that you get on the exponent of this game here. But then when you move here, you have to change it with its space. When you end up here, you end up with a 0, but then you have to add its partner. Its partner is the conjugate one, because it's time reversal, the Kramer pair is a different one. And then you have and then you follow the game, you go back, you get a 1, then you have an 11, which is the partner, and then you keep going like a little game, and then you see that you have to go all the way up, and you have to fill it with all these 12 lines to just end up with the beginning. So that means that this whole set of bands, that I call them combinatorial bands, or this band topology, it's a gigantic set. You cannot cut it. There's nowhere to go. But more interestingly, and this is what, of course, you see in this type of materials, this whole gigantic accordion. But more interestingly, Rafael asked me, what are the chiralities of these Weil points? Because they look like Weil points. They look like, or like linear. So we were puzzled a little bit, and Rafael, with all his power, computer power, was getting some numbers, and he was getting 1, and then at some point he got a 2 here. It looked like a 2. It's very complicated computation to find those chiralities, but it's not 1. One has to be very careful to see what it is. And so when he told me that it was not 1, I said, 1. So why is it a 2? So we were somehow, I just did the mathematics to see what is going on, and then have a little picture here. So we have two operators. What we're doing is what happens with two operators. The Hamiltonian is the blue things, it's the energy, and these are the eigenvalues of the Hamiltonian, while the eigenvalues of the rotation are these ones. And then you see the colors. This is what's going on. They need to, this band, which is blue and green, has to become blue and purple. And to do this, you get some topological jump. The topological jump, then, and of course, this is again, you can see you cannot open up the gap here because of this. This is what that doesn't allow you to open the gap, because you cannot cross here because the green will not continue to be green. If you kill Q, then you can open the gap. And this is what I meant, what you cannot do. So if I never tell anything to an experimentalist, but let's suppose I tell something to an experimentalist, then you cannot break the symmetry. Because if you break the symmetry, you open the gap. And then if you open the gap, you have another thing. And then you kill the invariant here, of course. So if I don't open the gap, then what goes on? So this picture somehow is telling me, imagine the yellow line is the path where we're moving in KZ. This in the middle is the Weil point, so I'm avoiding the Weil point. Around the point, there's a three-dimensional sphere. I put the three-dimensional sphere. So around the three-dimensional sphere, the energy, the Hamiltonian, is like something like this. Of course, one could think n equals 1, but not, because it depends on the eigenvalues of the operator. And it turns out that if I know the eigenvalues of the rotation operator, I can imagine what is n, because they have to be related. And if we do this, and then we simply see that when the chirality of the nodal point is simply congruent to the eigenvalues, to these numbers that I put here, you simply subtract, divide by 2, and that's the chirality. Of course, modulo 6, because of course there is some low principle. That's why I asked Emil, what is the highest number that you can get? So 11. 11 is quite a high thing when imagine that this 11 has to go like open up in small ones or something like that. Because of course these numbers could be, you might think, parallel 4. No, it's always 3, 2, 1, or 0. Never 4. Why? I suppose there's some minimal energy principle somewhere that I don't know where it is that forces the things to be the minimum number possible. But this is something that I don't know if it's true. You might correct. So then we did some computer programs once we know the answer, as Emil was saying. Once you know what the answer is what it has to be. And then suddenly the computer program now works, because once you know what is the answer, the computer works. And so we of course, we are somehow, look, I've learned many things. And so many times Rafael tell me, how do you know this is true? I said, because I just compute some things and this is the only way possible. There is not no other one. And I believe, I see Rafael's face, and he only believes me when he calculates it again, and he says, you're correct. I get the same number with my computer calculations. And I always think, what else could you expect? This is the only possible one. That's why it's a topological invariant. But as Emil was saying, well, the ultimate proof is not going to be my proposition, or this would be the experimental conclusion. Nevertheless, this is a good somehow example on which the image, what you see on your band, looks like this, but what it is not like this. It's something that if you took another path, you will see the exponent. But if you take this path, you will see it. And then one gets, wow, it's a tree, yeah, because we took the wrong path. Good. So we did again for another material, and I did my little combinatorics and blah blah. And we were somehow correct, but this was just somehow like an interlude to go to this Chern-Simons coupling term. So what is the idea here? So we cannot allow, in our perturbations, we cannot allow energy crossing the Fermi level, and depending on what symmetry I want to somehow put into play, I might get something or nothing. And the question that I want to solve is, what is symmetry I can put in, what not? So let me go to this table that if one is come from algebraic topology, one sees, wow, fantastic, because these are the homotopy groups of the O and these are the homotopy groups of the U. But it's put in a way in which the first time I saw it, what's going on? Why is it organized? So the thing is, we have these CPT symmetries, and they could be arranged in 10 different ways. In the two ones on which there's no time reversal or no chiral charge conjugation symmetry, we are in the complex K-theory setup, but that's the one that is the easiest to do, but that's the one you might want to use the least relevant, perhaps, because most of the cases interesting are here. So one can now use a lot of formulas in this one. There are not that many ones that apply for this case. But nevertheless, we're not in the complex K-theory case, and I'm going to focus mainly and only on the one on which we have spin orbit coupling, and we don't have the other two symmetries. And this is what is called A2, and then one can go and look at this table and take the dimension and do Z2. There is some invariant there that you might detect or not, and there's another invariant there that you might detect or not. This is what Emil was talking, weak invariants, strong invariants of three-dimensional materials, or the, depending on how you put the time reversal, two-dimensional invariant. Now, then this is a non-commutative object. Nevertheless, it's nicely non-commutative. So that's why we can put in an object that is, even though not commutative, it looks like commutative. Which is this appears as an invariant in the K theory, and I put a lot of letters. Real, because we're putting time reversal. N will give me, depending on which universe I'm talking about here, I need to move it up or down. The spin orbit coupling, which is given and the non-symmetry will give me some twist, and this is the point group, and this is depending on my dimension. All these things is quite easy to somehow define like this. I can define this object to you, but to tell you what it is on each group and that's not that easy, and perhaps soon some thesis will give me the table. But so far, I don't know the answers of all these groups, like in a computerized way, which maybe soon that somebody will do.
Yeah. What's tau? Is it a cocycle on the one group?
Yes, so this tau, because you need to go to the spin group, this is a Z2 extension, that's this spin orbit coupling. But the symmetry is because you don't have a section to, and this twist is also taking terms of this. So this is a twist that is not on the group. There is a twist that is on the group, and there's a twist that on symmetry is the group with, because you cannot get a section. So there are two twists around. And so, of course, the non-symmetry is a twist that is makes the spectral sequence more complicated. But it's there somehow. It's there in the crystal. If you have some symmetry that is the translation and something, then you have this non-symmetry, and this translation and something, then tells you that you need to somehow couple the group and the lattice element into another twist. This twist, let me just go back to really quick, because this is just what I said here in this one. Here, this is some coupling. You might not see it, but it's a coupling of the rotation with the translation. And this is the way you can trivialize the cycle, but in a local chart. And in this case, so it doesn't look here that there is a twist, but this is a twist. It's just somehow it's trivialized. Good. So the thing is, where does this table come from? And I'm going to focus on this one, and then just to see what can we learn from it and what don't we know from it. So it comes from Atiyah's reality theory. Atiyah was a mathematician, recently passed away. That among many things, he was the first one somehow to, in a coherent way, put a real structure on a complex vector model. So Chern and the world thinking for either you have some vector bundle that is real or a vector bundle that's complex or quaternionic. But it was Atiyah who first noticed, well, why don't you put some sort of involution, which I think of it as time reversal. Time reversal is acting on the space of momentum space, but it's also acting on the fibers. And so it's a new thing that is bigger than the standard K theory of real vector bundles, and also incorporates complex K theory in one object that is what he called Atiyah's, he didn't call it Atiyah's K theory, but it's nowadays called Atiyah's real K theory. So what nice things about it is that you think of it that if we have time reversal squared to 1 is what Atiyah defined as exactly what he defined as Atiyah's K theory. But there is this version, the quaternionic one. He didn't give it this name, but it's called symplectic. It's saying that it's written as quaternionic K theory. So whenever we have t squared equals to -1, we live in some universe of K theory that is this KQ that is shifted for by this one because periodicity, but doesn't matter. The point being is that there's a little formula that if I know how many coordinates are changed by this involution and how many coordinates are not changed, I can count them. And I can just take this r to the AB, namely you can think that one direction is not changed and the other direction is flipped. Then you can construct the sphere, the one point of quantification, and the invariance associated to this object, to this sphere where this involution is acting, it could be calculated by the ones that we knew before. It's just a matter of putting the coefficients correctly. And what are the ones we knew before? These ones. These were the calculations of the homotopy groups of the classifying space. Worse and worse and worse. These are just the invariants that could exist in real vector bundles and the invariants that exist in quaternionic vector bundles. And so these were calculations done before by Bott. And so what he put new is that you could also have some involution in the base that these ones didn't acquire. Because if you want to put what are the invariants of a sphere with whenever you have time reversal with involution together, then this is not doing anything on the base. Then you have an operator that squares to -1. Then you want to know a sphere here. A sphere subtracts 3, so it's 1, 2, 3. Well, you have nothing. So this table tells you if you have inversion and time reversal only, you have no bulk invariant. But so if you don't have it here, where do you have it? Well, you have it. And this was this fantastic finding of Kane. This is an L one. Kane invariant, which is we go and calculate, and this is the part of calculation. You go and calculate. You do all this with mathematics and too many letters. And the point is that what you get exactly is using this table, you can simply go and calculate when you have this is a sphere. Imagine that it's just one plane, but the time reversal flips both coordinates. You wrap this tori into a sphere, and this is the sphere, and then this is the bulk, and then you see you get 3 C2s and an extra C2. And these are the topological invariants if you only have time reversal, square to minus 1. Nothing else. There are no Chern classes, of course. They disappear. This is the only one. Nice. So whatever you do, whenever you have this invariant, this should appear. But now, what if you have time reversal broken? And it was somehow, and I put it in the next slide, that if you couple the time reversal with rotations or oscillations, that this might also give you some bulk invariant. And so Rafael told me this, and I went directly to calculate my K-theory groups, and I did this table. Doesn't matter what it is. The table is, I go and I have 2 different types of rotations. I can rotate around the z-axis, or I can rotate around some other axis. I rotate around some other axis. These are different cases, different types of invariant. One is around the z, another one is around the diagonal. And I use my previous information of Atilla, and then I see that I have, in all 3 cases, I get my bulk invariant, and the bulk invariant is Z2. But in the other different cases, I get some Chern classes that are there. That doesn't mean that they exist in any material, but they are there. It'd be nice to have a material that has them. And I have some other invariant here. Now, since all these Chern classes that appear here are never there in any material, then the calculation of the bulk invariant is easier. Otherwise, the Chern-Simons calculation would be difficult. But anyway, so since I know that there must be, these things must be quantized. What is going to be quantized? So let me just put the whole thing. So, and this is when you bring into the Lagrangian this magnetoelectric polarization that's written in this tensor way, somehow all right, somehow. Everybody reads the formula as everybody wants. No? I don't know any physics, so I see this and I see nothing. And I see this second Chern class. No? It's just telling me second Chern class. But if I go like this and I scratch my head, okay, what is this physically telling me? I have no idea what is physically telling me. I know what is the position of the electric field, the magnetic field. But then I see how does it behave, this object, when I integrate it over the, I need to put a time there. And then I see that it's periodic. This number is, you only get theta or theta plus 2 pi, or theta plus 4 pi, and then it's odd on the time reversal. Namely, if you apply time reversals to the whole system, then you get a negative of that. And that already tells me that if I get a negative of that, when I have time reversal, that the invariant is only possible to be, well, it's periodic, but it has to be also invariant under a negative sign. So the only options are 0 and pi. So it's fixed, it's blocked. If you have time reversal, the only option is theta and pi in the, and this object here, which is the Chern-Simons form, turns out that is the only bulk invariant whenever you have time reversal, and going backwards is exactly this one. No? The same one, just in this ugly table, is the same one. Now, one might expect that it's the same one in here. No, only if this Chern class vanish. Because the second Chern class could be the first Chern class and the first Chern class, but that doesn't matter. So most materials this doesn't exist, so we can only get there. So now it turns out that the way to calculate this is with this fantastic formula that Chern and Jeff Simons, who sponsors this institute, found when, which they imagined that this object, which is an antiderivative of the Chern classes, would provide a new topological, more than that, a geometrical invariant of some kind, of manifolds. In some sense, they do. If you couple it with a metric, then this Chern-Simons invariant detects information from metrics. But after working on them, they noticed that it was a secondary topological invariant, namely first invariant vanished, second Chern class vanished, and that there might be some torsion invariants around it, and this is the one. It's like on a surface, I have my Chern class vanishing, but I might have some holonomy that is just torsion holonomy, and that could be the torsion class, just disguised as a holonomy, as a torsion Holland. So this is, in some sense, this is the second Laplace, in some sense, just disguised as the antiderivative. And so if one looks at this, then one can imagine that, well, how can you make these things to be invariant in the sense that the only possible values are 0 and theta and pi, sorry. Well, if you happen to have time reversal coupled with a rotation or coupled with a translation will not change the value. A rotation will not change the value, but if it's coupled with a time reversal, automatically will again change the signs. And that means that if you may have time reversal symmetry broken, but if it's already kept with another rotation or translation, you might still have this thing to be fixed. So that means, and these objects are called axion insulators. And I don't know much about why the name axion insulators. Chern-Simons insulators. And anyway, so these were the symmetries that, well, look at the symmetries and you see that this doesn't involve anti-unitary operators, this doesn't involve anti-unitary operators, this is inversion. And symmetries that don't involve anti-unitary operators are simple. Simply go and fix point data information will tell you what it is. And the interesting ones, in my point of view, are the ones that involve time reversal operator because then you have some like real K theory there. So this was somehow written by Vanderbilt and colleagues that the symmetries that might protect the Chern-Simons term are these ones. And with Rafael, we went to see, more Rafael than me, to see a material that would have this and would see what happens. And so one way to detect, let me just put the whole thing to movie. One way to see whether you have one of these axion insulators is that this, see, there's, and I telling me that I don't know what is full boundary corresponds. Because whenever I think I know, then there is a material that doesn't fulfill it. So then that means my definition is wrong. So this is full boundary correspondence. Whenever you have all possible ways of knowing what happens in the boundary of the material, then you have full boundary correspondence. But what is the bulk boundary correspondence in a sense? Well, whenever you have time reversal symmetry, you know that you will have some energy crossings in the 2D material, and this you can do it computational, you can do experimentally, and then you have some conduction in the boundary of the 3D materials. But it turns out that in these other axion insulators or these other materials, you may find some energy gaps on the surfaces. And so this could be also measured or obtained by the anomalous Hall conductance that you can get on the surfaces, because this object here vanishes and then you get precisely the one that you were obtaining by the Chern-Simons coupling term. Now, we went more Rafael than me to find an object. This is the physics part of my talk, which if I am wrong, then blame Rafael. This material, which it exists as a Gedanken experiment, no? Because these objects may be impossible to use. I don't know if the physicists might tell me this, but every time we tell anybody these materials, they go, ha ha ha, this material is impossible.
Actually, I didn't know the NP.
Thorium. Like 300 in the.
It will probably kill you before you.
Exactly, if you use it, you will die. That's why it's very nice, because nobody will do the experiment.
They exist for like minus 10 exactly.
Exactly. So, but in this Gedanken experiment, computationally everything exists. So Rafael calculated everything, and somehow the things that I would say the people want to see is that they want to see some changes of colors of some object in the bands, which is given by the spin structure change or the orbital change. And it turns out that when we're looking at this change of colors close to the band gap, they didn't exist there. They existed there, far away from the Fermi level, which, since I don't know any physics, I told Rafael, doesn't matter, as long as they're there, who cares where they are? But maybe this does physically mean something which I don't know, but once you see them, you see, okay, there is a change of numbers in there somewhere, but we didn't find them on top. So there is some spin Hall conductance that is non-trivial, And it turns out that one can calculate the invariant with a specific formula that wants to be careful, similar to the two came maybe one, but one twisted. And so we did a model, and the model is very known nowadays when Hamiltonian, which simply goes and takes a Hamiltonian with the Higinio symmetries you have, and then you kill the symmetry. No? Then I learned it, and then when I didn't know it was difficult, when I knew, then you just put some gigantic Hamiltonian, you kill the symmetries, and then you have the symmetry you want. Of course, in this universe, it's like cheating because you are in the world of everything, and then you just move the parameters until you're in the world that you want, which is somehow contradictory with what I just said, that you're not allowed to move around, but in the way of the parameters we can do. So there is this change of phase here of the orbital, and so the thing that is important is that you cut this material in the different appropriate phases that has the symmetries of the crystal, and then you don't have any element that conduct. And once you go to the hinges, then you have conduction. And so this is a material that doesn't conduct in any surface, and it conducts in the hinges, in the triangle. If you ask me what is the use of that, don't know. But it's a beautiful thing because it's conducting here, and there is no surface that is conducting. So,
But what do you mean? If you cut it along 111, that's the surface that has surface states, or?
no surface states in any one. The states are on the hinges.
I see.
On the
Okay. The edges.
edges, I don't know how to call it, the saga or something.
Okay.
How is it called in English where the door opens and closes? Hinge, okay. You know, this is the right word. Good, so it's only in the hinges. So it's, but you see this Xicotencatl material that doesn't exist computationally has beautiful properties. Nevertheless, it fulfills all the things, and of course, one goes and calculates the example, as Emil was saying, that one can go and construct it, what is the answer. Again, this is knowing the symmetry, then I go calculate it, and then I'll see if I have it or not. If I know that I have it, I can give you an example. The simplest examples of all, and it's usually the same thing always with the Pauli matrix integrated in the Lie group. Good. So then we did C2T, and then at some point I was thinking, why can I not calculate on my K-theory this symmetry? This symmetry of there is alone. Nevertheless, the other one left. And I was thinking, well, it should be possible to do it calculation. So I'm supposed to be an expert in K-theory, but I had difficulties doing this thing. I didn't know how to do it. I didn't have the appropriate calculations on my hand. So then I told Higinio, which is a PhD student here in Mexico with Miguel, who is here present, that this is not a physics problem. This is, of course, a mathematics problem. Is what are the topological invariants of that symmetry? Which one would say, as a mathematician, no, it's just a simple example, it's a simple calculation. Nevertheless, we didn't have the appropriate theorem to even do it, because all the theorems that we were, the classical ones, didn't ever consider that the anti-unitary symmetries were coupled with the geometrical ones, and that time reversal was not there by itself. So we had to somehow go back to the original papers of Atiyah and Boyd and all these people and redo the construction of the K-theory to see what was going on. And it turns out that one has to simply go even further back to Wigner's book, Quantum Mechanics, and go to the calculation of the representations that he did in the last chapter, in most of the book. And one has to simply use his way of calculating representations that he basically did everything. And it was to simply define a magnetic group as a group which you have a group of symmetries, and some of the symmetries are anti-unitary and the other ones are not. But you don't have a splitting. The splitting is when you have time reversal alone. If you don't have time reversal alone, you may not have a splitting. So that means that you have to simply do it like a whole bunch of things together. And if you do that, then you define a representation. It's a complex vector space in which the ones that are linear are linearly, and the ones that are anti-linearly. There are irreducible ones. And what you do is you choose some subset of irreducible representations, the only ones that you want to allow. Namely, this is like the twisting. sense. You choose the appropriate representation, it's like the twisted. And then you can define the KT. This is just theoretically defined, black. But then what one needs is what in mathematics called, you want the spectrum, you want to know the homotopy groups of this thing. And the homotopy groups, it turns out that it was exactly the classical theorem, which is, if you want to know what happens on a point, which is this tenfold wave, that's what happens on points, on spheres. And this is how you fill the little z2s and z's on this tenfold wave. What you need to know is how many representations of real type, how many representations of complex type, how many representations of quaternionic type. The representation of complex type will give you the spectrum of KTU, a lot of Chern classes, integer things. The ones of real type will give you us having time reversal square equals 1, and the quaternionic type will give you us having time reversal square to -1. And this you can do because Wigner told us how to calculate the representations of all these magnetic groups. So when we go and take these 4 examples, which I just put here, which is t squared equals to -1, c2 to the square, and c for t, then we go and see what are the representations that we can play with. T squared equals -1 is basically what is the group of symmetries. The group of symmetries is Z4, but we are not taking the sign representation because that's not allowed, because we need to have this one, so there is only one representation. The map to Z2 is just 1 goes to 1, and the residual representation is this one, the common one where this is complex conjugation. And this is just quaternionic type. Again, this is just the simplex KQ, which we already knew, that's why we get this kind of invariant. If we do C2T, this squares to -1, this squares to -1, the whole square squares to 1. So we have an anti-unitary symmetry which squares to 1, which is like real type, and the simple representation is just complex conjugation. So we have KO, and then this is what we use to the other one. But then if we have C4T, this is C8, because this to the 4 is -1, so it's C8. But the only representations we can allow are the ones on which to the 4 are -1. There's only one. This is the original representation. If you do this to the 4, you get -1. And if you see this representation will be of complex type, because you do this square and you will get I and minus I. If I'm not mistaken. Yeah. And then you see that one is the complex conjugate representation of the other one, and automatically it becomes a complex type representation. Although it looks quaternionic, it's of complex type, and therefore the invariance that I get is KU Chern classes only is the only thing that I can get, and from these Chern classes, with an extra step of the Hirsebruch spectral sequence, one can show that there's no invariant in the bulk. But it depends heavily on knowing this part. Depends heavily on knowing what is exactly the K invariance, like the temporal way universe, like homotopy groups. And with the homotopy groups, I can go and do a simple, simple in some sense, argument to show that there are no invariants. Namely, what does this say then? This say that this symmetry fixes the theta term, but not to pi. It will fix it to 0, because pi will not appear. Because if it were pi, I would detect it, and I'm not detecting. There's no topological invariant associated with it. So, just to finish, so as Miguel was saying, so K theory is it's just a word that is very ugly. Okay, would be a better word to this topological invariance of vector bonds. So K, what is K? K stands for a letter that they used. Many, like Higinio Serrano decided to use that letter. But what it says is that it was what in what K? Classic.
I think in German.
Yeah. Although he was speaking French. Anyway, so from classes, but it has a name that may look like a complicated thing. It is exactly the invariance of vector bonds, whatever they are. But whenever you add symmetries, the invariance may flip, may go somewhere else, may jump around. So even though we have this tenfold way is associated explicitly to having time reversal. You might have another type of symmetry, like with time reversals associated, the tenfold way doesn't apply. It applies another tenfold way, which has to be moved around. And so if I take any generic magnetic material, then I need to see what is the appropriate tenfold way table, which I don't have it, but the symmetries at least on which it involves time reversal and rotation, we know exactly. 2 of them, yes, the other one doesn't protect anybody, even though it forces to be 0, the Chern-Simons couple term. But of course, there are more. There are time reversal coupled with translation. And this brings us to the world of twisted K theory that we haven't calculated. And there is even more. We can have time reversal with translation and rotation. And this one, again, we haven't calculated. But this is a calculation to tell us whether we have the symmetry or not, and to know exactly what symmetry protects what, and what symmetry protects not. So this is the subject of the thesis of Higinio. He's doing the mathematics of it. And this is just, again, to me, it's a problem appearing in physics. We don't have the tools to do it. Like, what is the topological invariant to do it? And so we look around, and there's no way to do it unless we go backwards and we fix this what we didn't do before, and we bring it, and of course the same tools, the same K theories that we were saying, but the calculations sometimes need to be worked properly to be able to bring some example. And this is what I was going to tell you. Thank you very much. 5 minutes.
Thank you, Bernardo.